1.3. Okay, we want to go a little bit deeper into the mechanics of how Dirichlet boundary conditions are imposed in NGSolve. Okay, so here's the idea. It's what we learn in finite domain textbooks. If you have non-homogeneous Dirichlet data like this on a part of the boundary, we extend the Dirichlet data from the boundary parts into the interior of the domain and convert the boundary data into a volume source, thereby reducing the non-homogeneous Dirichlet problem into a homogeneous Dirichlet boundary condition problem. Okay, and then we'll discuss what is happening in the homogeneous case. And of course, there is we will look at these steps, these first three steps in detail. And if you don't care about all these details and you just want to get the thing done, then you just go directly to the end of the tutorial, and there is an automatic utilities. It's something like solve BVP or something, and it'll do it for you. But if you want to understand what's happening behind the scenes, you look at these three steps that I'm going to explain now. Okay, so again, our famous unit square. It has four boundary parts: bottom, right, top, and left. And suppose we want to impose non-homogeneous Dirichlet boundary conditions on the left and right. Okay, so first we declare that, let it be known to the finite domain space that left and right are going to be Dirichlet boundary segments. Okay, and now there is a point of potential confusion. Here's a space where there is the Dirichlet flag set, and here's a space without any Dirichlet flag set. So you would think that the number of degrees of freedom of these two spaces are different because one has Dirichlet boundary conditions and the other doesn't. But if you ask for n DOFs, or the number of degrees of freedom, you get the same number, and then you are upset. And so you should not be, because the way the Dirichlet boundary condition is imposed is through another facility called free DOFs. Okay, free DOFs says what degree of freedom is free versus constrained. When you have a Dirichlet boundary condition, at a certain point, then that point is constrained to have only the values the Dirichlet boundary condition allows it to have. So that's a constraint node. When it's not constrained, it's free. Okay. So the number of free DOFs, or this entire array of free DOFs, you can print that out. And if the print looks a little funny, you have to this whole thing. The first three lines is one vector. So we're just printing zeros and ones as a bit array, but only 50 characters are printed per line. So these three together makes one bit array. Okay, and as you can see, the FS2 space, where we did not set any Dirichlet boundary condition, has all degrees of freedom free. The other one, FES, where left and right was set to be Dirichlet boundary condition, you have a bunch of zeros there, indicating that some of these degrees of freedom are not free, or they have Dirichlet constraints. Okay, so this free DOFs is important for how the Dirichlet boundary condition is implemented. The next thing is the extension of boundary data. So if you're given a G that's supposed to be the boundary data on the boundary, we have to extend it inside the domain and as this function, U sub D, the extension of the Dirichlet data, and then write the original solution as something with zero boundary conditions and this extension. Okay, so once you do that, you plug this back in to here and move the data, Dirichlet data, to the other side, and you just need to solve a problem with zero Dirichlet boundary conditions. Okay, so in order to implement this approach, we need to know how to compute U sub D. That's the first question here, and then the next point is how do you solve this for this zero Dirichlet boundary condition problem. Okay, so the first point about how do you get the extension. Suppose suppose we're given a data like this, sine of the y coordinate. Okay, and we want to set this. We want to create an extension. The same facility we saw before called set gives you an extension of this boundary data. Okay, so we take a grid function and we set this grid function using this sine y, which is a coefficient function, but now we say that set it only on the boundary. So this is different from the set we saw before, in that we provided this argument. And then when you draw this function, you see that the values of sine y has been imposed on the boundary, and this extension function is cut down to 0 in a strip of elements adjacent to the boundary, because all of these blue areas are 0. Okay, and the keyword B and D is what tells it to do that, to just set the coefficient function on the boundary and then cut it down to 0 in this one strip of elements. Okay, now so we did the extension. The next step is to solve for the problem without any boundary conditions, now that we know the extension. And for that we make the bilinear form, and then we look at how do you compute this U0. So one way to understand it is to separate the degrees of freedom into free and Dirichlet constraint degrees of freedom. Write up the matrix, partition the matrix using these indices corresponding to free degrees of freedom and the Dirichlet degrees of freedom, and then write this equation down, or this equation down in this block partition form. And what we want is this thing. This is the values of U0 at all the vertices where its value is not 0, and from this equation you can solve for that, and that's what's happening here. So you compute f minus ud, which is this thing, and then you have to do the inverse of f, but only on the free degrees of freedom. So you need a way to say that don't try to take the inverse of this whole thing, but just do the inverse on the free degrees of freedom, and the syntax for that is coming below after we make this right hand side. Okay, now we have this modified right hand side R, and taking this inverse in the free degrees of freedom is accomplished by this, by providing an argument to the inverse, to ask the inverse to do the inverse considering only the free degrees of freedom and ignore all the constraint degrees of freedom. Okay. Okay. So once you do that, you have the solution, and you can do all of this all at once using this BVP facility inside the solver's submodule. All you have to do is to provide it with a bilinear form, the linear form, and some sort of preconditioner. You could give any of the ready-made preconditioner, and that'll do it. Okay. Questions?
Don't forget the plus equals, because I think that's one of the most common mistakes in this, that you forget to add it to the Dirichlet data, and I very often see an equal here and then.
Yeah, you've answered a lot of forum questions on this.
Can you do me a favor and deform the solution there for a second?
Deform the solution? Okay.
Because I'm curious, and this has been a thing I think Dow told me, which is that it appears where you haven't otherwise set Dirichlet conditions or interpolated something, you have Neumann conditions as default.
Yes.
Is that the case? And is that the case for every space, that there's some, when you're not doing Dirichlet, there's some default condition?
Yeah, so this is another finite element question. So when we integrate by parts and make the variational formulation, the Neumann condition is in the variational formulation. It's a natural boundary condition. So if you don't do anything, that's a natural boundary condition that is imposed.
I see. So if you tried to catch that, you'd have to do boundary things in your bilinear forms and stuff.
if you have a non-homogeneous Neumann data, then you would need an additional integral.
Yeah.
If there is no additional boundary integral, you're just doing du dn equals 0.
Already in the finite element space, you say this is a Dirichlet boundary. There you have set constraints.
Yeah, we don't say Neumann equals this. We only say Dirichlet equals this because only the essential boundary conditions are to be imposed in the space. Any further? Okay. Am I going too slow or?